This presentation is titled From Principles to Practice, a visual guide to quantum optics and information experiments. It serves as a technical blueprint covering the hardware, physics, and data signatures behind 9 fundamental quantum laboratory setups. The cover image features a nonlinear crystal mounted on an optical breadboard, with a blue pump laser being split into 2 red output beams, a visual metaphor for the experiments that follow. The goal of this series is to bridge abstract quantum theory with the actual physical equipment used to test it in a real laboratory. Each slide maps a specific quantum phenomenon to the components required to observe it experimentally. By studying these blueprints, researchers and students can translate quantum mechanical principles into concrete laboratory procedures. This presentation was generated using Notebook LM as a structured educational resource. It is designed for audiences with some prior background in quantum mechanics or photonics. The experiments covered progress from single-qubit state preparation all the way to multi-photon quantum computing gates. Together, these 9 setups form a complete foundation for understanding optical quantum information science. This slide introduces the 5 core physical components that appear throughout all quantum optics experiments in this series. The first component is the waveplate set, consisting of a half-wave plate and a quarter-wave plate, which together perform state preparation by applying single-qubit rotations, such as Hadamard and phase gates, through polarization manipulation. The second component is the polarizing beam splitter, or PBS, which serves as the primary measurement device by projecting quantum superpositions onto the computational basis states, KET-H or KET-V. Third is the beta barium borate crystal, commonly abbreviated BBO, which functions as an entanglement source through spontaneous parametric downconversion, splitting high-energy pump photons into entangled pairs. Fourth are the avalanche photodiodes, or APDs, which are single-photon detectors capable of registering individual photons with very high timing resolution. The fifth component is the time-correlated single-photon counting module, or TCSBC, which performs coincidence counting by recording simultaneous detection events across multiple detectors. Together, these 5 instruments, waveplates, polarizing beam splitter, BBO crystal, avalanche photodiodes, and the TCSBC module, form the universal hardware alphabet of quantum optics. Every advanced protocol in this presentation is built from these basic building blocks. Understanding each component's role is essential before proceeding to more complex multi-photon experiments. The TCSBC formula shown references the quantum partition function formalism, grounding these optical tools in fundamental quantum statistical mechanics. Quantum state tomography is the process of taking a complete mathematical snapshot of an unknown quantum state using repeated, statistically analyzed measurements. The experimental setup consists of an unknown polarization state entering a rotating half-wave plate, followed by a polarizing beam splitter, and then 2 detectors labeled DH and DV for horizontal and vertical polarization components, respectively. By rotating the waveplate to different angles, the measurement basis is systematically changed across the X, Y, and Z axes of the Bloch sphere. The Bloch sphere shown at the top of the slide visualizes all possible single-qubit states as points on or inside a unit sphere, with the 3 axes labeled as the expectation values of sigma x, sigma y, and sigma z. A pure state sits exactly on the surface of the sphere, while mixed states lie somewhere inside it. The density matrix of any single-qubit state can be written as rho equals 1/2 times the quantity identity matrix plus r dot sigma, where r is the Bloch vector and sigma is the Pauli vector operator. This formula is the mathematical reconstruction target. The goal of tomography is to experimentally determine all 3 components of the Bloch vector r. Each measurement basis setting provides one component of the Bloch vector from the ratio of count rates observed at detectors DH and DV. The process requires many repeated measurements on identically prepared states, not a single shot, because quantum measurement is inherently probabilistic. Quantum state tomography is the foundational diagnostic tool used to verify the output of any quantum gate, entanglement source, or state preparation procedure. This slide presents the experimental setup for a quantum random number generator, which exploits the fundamental indeterminism of quantum measurement to produce certified random bits. A photon is prepared in the diagonal superposition state called ket+, which equals ket h plus ket v, divided by root 2, meaning it has an exactly equal probability amplitude for horizontal and vertical polarization. This photon is then sent through a polarizing beam splitter aligned in the rectilinear basis, which routes it to either detector 0 or detector 1, depending on the measurement outcome. The outputs at both detectors are random binary sequences that are fundamentally unpredictable, not merely computationally hard to predict. The key physical principle here is the Born rule. In quantum mechanics, there is no hidden variable determining which detector fires. The randomness is ontological, meaning it is woven into the fabric of physical reality itself. Unlike algorithmic pseudorandom number generators, which are deterministic sequences that merely appear random, this source produces genuine randomness guaranteed by the laws of physics. The statistical quality of the output is characterized by Shannon entropy, written as capital H, and because both outcomes occur with probability 1/2, the entropy reaches its maximum possible value of exactly 1 bit per photon. This maximal entropy means no information is wasted, and the output bits are perfectly unbiased. The coin graphic superimposed on the beam splitter is a conceptual reminder that each photon detection event is as random as a fair coin flip. This experiment is the hardware foundation for certifiably random number generation used in cryptographic and simulation applications. This slide compares 3 fundamentally different types of light sources using the Hanbury-Brown and Twiss experiment as the diagnostic measurement tool. The Hanbury-Brown-Twiss experiment measures the second-order photon correlation function, written as g² of 0, which quantifies whether photons tend to arrive in bunches, randomly, or strictly one at a time. Thermal light, such as from an incandescent bulb, has a g² of 0 equal to 2, meaning photons tend to cluster and arrive in pairs. This phenomenon is called photon bunching and arises from the chaotic, multi-mode nature of thermal emission. Coherent light from a laser has a g² of 0 equal to exactly 1, indicating Poissonian photon statistics. Photons arrive completely randomly with no temporal correlation, which is the defining characteristic of a coherent state. Single photon light, generated via spontaneous parametric downconversion, has a g² of 0 equal to 0, meaning the probability of 2 photons arriving simultaneously at the detector is identically 0. This is called photon antibunching and is a purely quantum phenomenon that is impossible in classical wave optics. Each light type produces a distinct Hanbury-Brown-Twiss correlation signature plotted against delay time tau. Thermal shows a peak at tau equals 0, laser shows a flat horizontal line at 1, and single photon shows a sharp dip all the way down to 0 at tau equals 0. The g² of 0 equal to 0 signature is definitive experimental proof that light is quantized into discrete photons. This experiment, originally designed for stellar intensity interferometry in astronomy, became one of the foundational tests of quantum optics. The 3 signatures serve as a quality control benchmark in any quantum photonics laboratory. Understanding light source statistics is essential for certifying the purity of a single photon source used in downstream quantum information protocols. The Hongou-Mandel effect is one of the most striking demonstrations of quantum interference, occurring when 2 perfectly identical photons arrive simultaneously at a 50-50 beam splitter from opposite input ports. In the experimental setup, a motorized delay line on one input arm is used to tune the relative arrival time, and therefore the temporal overlap between the 2 photons. Two detectors monitor the two output ports of the beam splitter, and a coincidence counter records how often both detectors fire simultaneously within a narrow time window. When the delay tau is large, the two photons are distinguishable in time, and coincidences are observed at the expected classical rate. However, when tau equals 0 and the photons are perfectly temporally overlapped, and therefore completely indistinguishable, the coincidence count rate drops all the way to 0, producing the signature feature called the Hongou-Mandel dip. The physical explanation lies in bosonic symmetry. For two indistinguishable photons at a beam splitter, there are four possible path combinations. Both reflect, both transmit, photon 1 transmits while photon 2 reflects, or photon 1 reflects while photon 2 transmits. The two crosspath probability amplitudes carry opposite signs, causing them to cancel exactly through destructive quantum interference, leaving only the two cases where both photons exit from the same output port together. The width of the Hongou-Mandel dip is directly related to the coherence length of the photons, making this experiment a precise measurement tool for photon indistinguishability. High photon indistinguishability, as revealed by a deep and narrow dip, is a critical requirement for linear optical quantum computing gates. This bosonic bunching effect is the direct physical foundation for the probabilistic CNOT gate construction presented in a later slide. This slide details the physical mechanism for generating polarization-entangled photon pairs using spontaneous parametric downconversion, abbreviated SPDC. A high-energy blue pump laser beam is focused into a beta barium borate crystal, abbreviated BBO, which is a birefringent nonlinear optical medium. Inside the crystal, with very low probability, a single high-energy pump photon spontaneously splits into two lower-energy photons called the signal and the idler, which are emitted symmetrically on either side of the pump beam axis. By engineering the crystal phase-matching geometry, the signal and idler are produced in the polarization-entangled Bell state known as phi+, which equals the sum of ket HH and ket VV divided by √2. This state means that neither photon individually possesses a definite polarization. The two-photon system exists in a quantum superposition of both photons being horizontally polarized and both photons being vertically polarized simultaneously. Yet when either photon is measured and found to be in a definite polarization state, the partner photon instantly acquires the same polarization, regardless of the spatial separation between them. The BBO crystal, together with its entangled signal and idler outputs, is introduced here as a standardized module, represented by a compact icon in subsequent blueprints. SPDC is currently the most practical and widely used method for generating entangled photon pairs in a tabletop quantum optics laboratory. This entanglement source is the essential hardware prerequisite for the Bell inequality tests, quantum teleportation, and entanglement-based quantum key distribution protocols that follow. The slides note on progressive disclosure signals that this module will recur throughout the deck as a core building block. This slide presents the experimental blueprint for testing Bell's theorem using the Klosser-Horn-Shimony-Holt inequality, commonly abbreviated CHSH. The setup consists of the BBO entanglement source at the center, distributing one entangled photon to Alice's laboratory on the left and one to Bob's laboratory on the right. Each laboratory contains an electro-optic modulator, or EOM, for fast and random measurement basis switching, followed by a polarizing beam splitter and two photon detectors. Alice randomly chooses to measure at either angle alpha equal to 0 degrees or alpha prime equal to 45 degrees, while Bob randomly measures at either beta equal to 22.5 degrees or beta prime equal to 67.5 degrees. The CHSH parameter S is defined as the absolute value of E of a comma B minus E of a comma B prime plus E of a prime comma B plus E of a prime comma B prime, where E denotes the correlation expectation value for each pair of measurement settings. Under classical local realism, the assumption that measurement outcomes are predetermined by hidden variables and no influences travel faster than light, this parameter S must always be less than or equal to 2. Quantum mechanics predicts a maximum achievable value of S equal to 2 times root 2, which is approximately 2.82, clearly exceeding the classical bound. A measured value of S greater than 2 is the experimental proof that no local hidden variable theory can explain the observed correlations in nature. This experiment was first theorized by John Bell in 1964 and has since been performed in increasingly loophole-free versions by multiple research groups worldwide. The successful violation of S greater than 2 is the definitive empirical demonstration of quantum non-locality, what Einstein famously and skeptically called spooky action at a distance. Quantum teleportation is the protocol for faithfully transferring a complete quantum state from one location to another, without physically transporting the particle that originally carried that state. The architecture is divided into 4 functional zones arranged from left to right across the optical table. Zone 1 is entanglement distribution. The BBO source generates a Bell pair and sends 1 photon toward Alice's measurement station and 1 toward Bob's correction station. Zone 2 is Bell state measurement. Alice combines her unknown input state, labeled ket psi, with her half of the entangled pair at a beam splitter and polarizing beam splitter, performing a joint measurement that projects the 2 photons onto one of the 4 Bell states. 2 detectors in Zone 2 register the measurement outcome, which is encoded as 2 classical bits with possible values: 0 to 0, 0 to 1, 1 to 0, or 1 to 1. Zone 3 is the classical channel. These 2 classical bits are transmitted to Bob through an ordinary classical communication link. This required step is why teleportation cannot be used to send information faster than light. Zone 4 is unitary correction. Based on the 2 bits received from Alice, Bob applies one of 3 possible waveplates, labeled X, Y, or Z, to his photon, performing the appropriate quantum gate operation to reconstruct the original state ket psi perfectly at his location. Crucially, no quantum information travels through the classical channel. The state is reconstructed at Bob's side using the pre-shared entanglement as the quantum resource. Each teleportation event consumes exactly 1 Bell pair, which cannot be reused. This protocol is the fundamental mechanism underlying quantum repeaters and future quantum network nodes in a global quantum internet. This slide details the correction logic that Bob must apply to his photon after receiving Alice's Bell state measurement result, and connects the protocol directly to the quantum no-cloning theorem. The correction lookup table has 4 rows corresponding to Alice's 4 possible measurement outcomes. If Alice detects the result 0 to 0, Bob applies the identity gate, meaning his photon already carries the correct state and no action is needed. If she detects 0 to 1, Bob applies a phase flip gate, also known as the Z gate. If she detects 1 to 0, Bob applies a bit flip gate, also known as the X gate. If she detects 1 to 1, Bob applies both a bit flip and a phase flip together, which corresponds to the gate negative I times Z. The visual on the right side of the slide dramatizes the no-cloning theorem. The original input state ket psi at Alice's source is shown fragmenting and disintegrating at the moment of measurement. This destruction is not an engineering flaw. It is a physical necessity enforced by the quantum no-cloning theorem, which states that an arbitrary, unknown quantum state cannot be perfectly duplicated by any physical process. If copying were possible, Alice could retain the original while Bob simultaneously reconstructed an identical copy. But the no-cloning theorem strictly forbids this. The teleportation protocol is consistent with the no-cloning theorem, precisely because the original state is irreversibly destroyed during Alice's Bell state measurement before Bob's copy is completed. The 2 classical bits carry no information about the quantum state itself. They only tell Bob which of 4 unitary corrections to apply to recover it. This correction step is what makes the entire teleportation protocol deterministic and always successful. given the pre-shared entanglement and the classical communication channel. This slide presents the BB84 quantum key distribution protocol, the first and most widely implemented quantum cryptographic scheme, proposed by Bennett and Brassard in 1984. The protocol operates in 4 sequential steps between 2 communicating parties, conventionally named Alice and Bob. In step 1, Alice uses a photon source and randomly selected waveplates to prepare each photon in one of 4 possible polarization states, drawn from 2 measurement bases: the rectilinear basis, denoted by a plus symbol, or the diagonal basis, denoted by a times symbol. In step 2, Alice transmits these photons one by one through the quantum channel toward Bob. In step 3, Bob independently and randomly selects a measurement basis for each incoming photon and records his detection outcomes. In step 4, Alice and Bob compare their chosen bases over a public classical channel. They discard all measurements where they used different bases and retain only the results where their bases matched, forming the raw secret key. The example table shown illustrates one specific case. When Alice used the rectilinear basis with bit value 1, but Bob measured in the diagonal basis, the result is discarded because the bases did not match. The security of BB84 derives directly from the Heisenberg uncertainty principle. Any eavesdropper who intercepts a photon must perform a measurement in some basis, which inevitably disturbs the quantum state and introduces detectable statistical errors into the key. This gives BB84 information theoretic security. Its protection is guaranteed by the laws of physics, not by the assumed mathematical difficulty of a computational problem. BB84 is therefore immune to attacks by future quantum computers, unlike classical public key cryptographic systems such as RSA. This slide demonstrates why any eavesdropping attempt on a BB84 quantum channel inevitably leaves a detectable physical trace, using the intercept-resend attack as the illustrative example. The 5 steps of the attack are shown sequentially along the beam path. In step 1, Alice transmits a photon prepared in the ket plus state, which is encoded in the diagonal basis. In step 2, Eve, the eavesdropper, intercepts the photon with her intercept-resend module and measures it in the rectilinear basis, a wrong basis choice made with 50% probability. In step 3, Eve's measurement causes the quantum state to collapse irreversibly to ket 0, that is, the horizontal polarization state, because the rectilinear basis measurement forces the superposition to resolve into a definite outcome. In step 4, Eve resends a new photon prepared in the ket 0 state toward Bob. In step 5, Bob measures in the diagonal basis as intended, but since the photon is now in a definite rectilinear state, not the original diagonal superposition, Bob has a 50% probability of recording the wrong bit. This error accumulates across the transmitted key, injecting a quantum bit error rate, commonly abbreviated QBER, of exactly 25% into the sifted key. A QBER this large is a definitive fingerprint of eavesdropping, since a noiseless quantum channel would produce a QBER near 0. Alice and Bob detect Eve's presence by sacrificing a publicly disclosed subset of their key for error rate estimation. If the measured QBER exceeds a safe threshold, they abort the protocol and discard the key entirely. This measurement-induced disturbance is not a technological weakness, but a fundamental consequence of the quantum measurement postulate. No technological advance can allow Eve to intercept and measure quantum states without disturbing them, making the detection of eavesdropping an absolute physical guarantee. This slide presents the optical construction of the C0 gate, the fundamental 2-qubit entangling gate required for universal quantum computation. In solid-state systems or ion-trap quantum computers, a deterministic C0 gate can be implemented directly, but photons in linear optical systems do not naturally interact with one another, making a direct deterministic 2-qubit gate impossible without additional quantum resources. The linear optical C0 gate, shown here, works around this limitation by introducing 2 ancillary photon rails, additional photon modes beyond the control qubit and the target qubit, along with an array of beam splitters and phase shifters. The gate exploits a principle called measurement-induced nonlinearity. When the ancillary photons are detected by the heralding detectors, highlighted with bright borders on the diagram, the detection event itself applies the required nonlinear transformation conditionally to the control and target qubit photons. A successful heralding event corresponds to the correct detection pattern that signals the gate has performed the swap of ket 1 to 0 to ket 1 to 1 and vice versa, as labeled on the output side. The fundamental limitation of this approach is that the gate succeeds only probabilistically, with a success probability of approximately 1 in 9, or about 11% per attempt. This low success rate is a significant practical challenge for scaling linear optical quantum computers to useful sizes. The Nil-Laflamme-Milburn theorem, published in 2001, showed that scalable linear optical quantum computing is possible in principle using large numbers of ancilla photons and feed-forward adaptive measurements, but requires substantial resource overhead. The slide caption emphasizes that the non-determinism of this gate is an intrinsic consequence of the linearity of all optical elements used, not an engineering imperfection that can be eliminated with better technology. Fault-tolerant photonic quantum computing architectures address this challenge through photonic error correction and cluster state approaches. This slide provides a structured comparative summary of the 3 advanced quantum optical protocols presented in this series: quantum teleportation, quantum key distribution using BB84, and the linear optical C0 gate. The comparison matrix has 5 columns: the protocol name, its primary objective, whether entanglement is required, whether classical communication is required, and the resulting success rate. Quantum teleportation has the objective of moving quantum states from one physical location to another. It requires pre-shared entanglement as a resource. It requires a classical communication channel to transmit the 2-bit Bell state measurement outcome. And it operates deterministically, meaning it always succeeds perfectly given both resources. Quantum key distribution, using BB84, has the objective of sharing a secret cryptographic key between 2 parties. It does not require entanglement, it does require a classical channel for basis reconciliation and error estimation. And it is deterministic in the sense that a usable secret key is always established after the sifting and privacy amplification procedures. The linear optical C0 gate has the objective of performing quantum computation. It requires ancillary entanglement in the form of ancilla photons. It does not require any classical communication channel. But it is inherently probabilistic, with a success rate of approximately 11% per gate operation. The matrix reveals a fundamental trade-off in quantum information processing. Deterministic quantum protocols require both entanglement and classical communication working in concert, while purely optical computation sacrifices determinism to operate without a classical communication channel. This comparison table is a useful design reference for understanding the resource requirements and architectural constraints of different quantum information tasks. It makes clear that entanglement and classical communication are both expensive resources, whose careful combination unlocks the most powerful deterministic quantum capabilities. This final slide synthesizes the entire presentation by showing how just 4 core optical components serve as universal building blocks, sufficient to realize all the quantum phenomena and protocols discussed throughout this deck. The 4 hardware elements are waveplates, comprising the half-wave plate and quarter-wave plate, polarizing beam splitters, the SPDC crystal for entanglement generation, and avalanche photodiode detectors. Waveplates enable single-qubit gate operations by rotating the polarization state of individual photons in a controlled and programmable way. Polarizing beam splitters enable 2-qubit interference effects, including the Hongou-Mandel effect, Bell state measurements, and single photon detection in defined polarization bases. The SPDC crystal generates entanglement on demand by producing polarization-correlated bell pairs from a pump laser through spontaneous parametric downconversion. Avalanche photodiode detectors provide the measurement capability that collapses quantum states, registers single photon events, and enables coincidence-based correlation experiments through the TC-SBC electronics. Together, these four tools are sufficient to implement every protocol in the series: single qubit state tomography, quantum random number generation, Bell inequality testing, quantum teleportation, BB84 key distribution, and the linear optical probabilistic C0 gate. The central image shows a fully populated optical table where all these components are interconnected, representing the integrated complexity of a real quantum photonics laboratory. The caption emphasizes that every counterintuitive quantum phenomenon, from non-locality to teleportation, ultimately reduces to the careful orchestration of this finite set of physical building blocks. This demystifying perspective is the core message of the entire presentation. Quantum optics is not magic, but precise engineering conducted at the level of individual photons. The deck invites the audience to cross the bridge from abstract principles to concrete physical practice, from theory to experiment, from equations to optical tables. End of narration script. Total slides, 15. Estimated TTS duration at 140 words per minute, approximately 50-55 minutes.